The global manufacturing supply chain is a physical architecture problem, not an economic theory. If you have ever wondered how China transformed from a low-cost assembly floor into the global manufacturing powerhouse and elite tech leader it is today, the answer lies entirely in the physical plumbing. In 1980, the Western world faced a calculation: sustain expensive domestic factory floors with union labor, pensions, and environmental regulation, or outsource assembly to jurisdictions where labor cost $2 per hour and regulatory burden was negligible. They chose outsourcing. This was a fatal miscalculation of physical geography. The West kept design, kept intellectual property, kept the brains at home. They exported only the muscles, the low-margin assembly work. This seemed rational. It was catastrophic. By the end of this video, you will learn the exact three mechanisms behind this shift: the physics of geographic compression, the multi-billion-dollar postal loophole, and the hazardous chemical processing infrastructure that creates an unbreakable choke point. You will understand why the Western world is now physically trapped inside a supply chain they designed themselves. During the 1980s and 1990s, Western corporations dismantled domestic manufacturing infrastructure. Ford, GE, Intel, and Motorola shuttered production lines across the American Midwest, Southeast, and California. The financial logic was brutal. Every dollar spent on domestic labor and compliance reduced quarterly earnings per share. Wall Street rewarded outsourcing with stock appreciation, pension liabilities vanished, real estate became capital gains. The mathematics were perfect for quarterly returns and catastrophic for long-term structural capacity. Into this vacuum stepped China. Chinese planners viewed incoming Western contract manufacturing work not as profit, but as capital investment. Between 1990 and 2005, multinational corporations shipped an estimated $500 billion in manufacturing contracts to China. Chinese manufacturers and government planners did not extract that capital as dividends. They reinvested nearly all of it into physical infrastructure. They built factories, purchased precision tooling, trained engineering workforces, constructed ports and logistics networks. While Western corporations extracted capital from manufacturing and redirected it into financial services, Chinese manufacturers poured capital into physical density. The Western strategy was asset light: minimize capital expenditure, maximize quarterly cash flow. The Chinese strategy was asset heavy: maximize capital expenditure, build monopoly-grade infrastructure. By 2005, China was no longer a low-cost assembly outpost. It was becoming a vertically integrated superpower with capital equipment, supply chain density, and logistical infrastructure Western competitors did not possess. This infrastructure density would become the mechanism that turned an initial cost advantage into an irreversible structural monopoly. The fundamental physics of supply chain efficiency is simple. Transit time equals hidden cost. A component crossing the Pacific Ocean via container ship incurs 14 to 18 days of dead time, where it generates zero value. A component requiring customs clearance at multiple international borders adds 3 to 4 days of latency. A component sitting in a warehouse waiting for international freight represents working capital locked in inventory, capital that sits idle, generating no return. Imagine building with Legos. If every piece sits in a single sandbox, you grab red brick, snap it to blue, grab yellow, assemble the structure in 12 minutes. Your supply chain velocity is optimized. Now scatter those pieces across 12 countries. Red bricks manufactured in Taiwan, blue bricks in South Korea, yellow bricks in Malaysia, casings assembled in Vietnam, battery packs in Indonesia, magnets in Thailand, testing equipment in the Philippines. Each piece must travel 2,000 to 8,000 miles via international freight, requiring 2 to 4 days of ocean transit, 1 to 2 days of customs clearance, and 1 to 2 days of warehouse handling at each port. Your supply chain now consumes 14 to 21 days just moving physical components between factories. This is the Western model. It optimizes for quarterly cost reduction, not for manufacturing velocity or engineering iteration speed. Shenzhen operates on completely different physical principles. The industrial cluster occupies approximately 4 square miles. Within that radius sit over 50,000 factories and manufacturers. Chip fabrication plants operate on the same street as connector manufacturers. Magnet processing facilities are 6 blocks from assembly plants. Circuit board testing centers sit in adjacent buildings. The final assembly and packaging warehouses are a 15-minute drive from component suppliers. Component transit time inside Shenzhen, 12 minutes. This geographic compression creates massive compounding effects on engineering velocity and product iteration speed. When a Western engineer in California detects a design flaw Monday morning, it must travel through email chains, design revisions, and specification documents before reaching a Vietnam manufacturing partner. By Wednesday, the problem reaches production. Factory floor modifies tooling Thursday. New units build Friday. Quality testing happens the following week. Corrective production ships via 18-day ocean freight. The engineer receives corrected units approximately 30 days after identifying the initial problem. In Shenzhen, the same feedback loop takes 6 hours. An engineer spots a flaw in the morning. By lunch, the design file is revised. By mid-afternoon, the factory has received the specification change. By evening, new tooling is configured. By the next morning, 10,000 corrected units are produced. By midday, quality testing confirms the fix. This is not work ethic. This is pure physics. Shenzhen executes engineering iterations 26 days faster than the Western model. Over a single year, this means Shenzhen completes 13 full engineering cycles, while Western supply chains complete 1. This is structural advantage encoded directly into geography. China's entry into the World Trade Organization in 2001 hypercharged the utilization of a structural arbitrage framework built into global mail infrastructure. The Universal Postal Union, established in 1874, sets the prices national postal services charge each other for international mail delivery. In 1994, the UPU introduced a critical classification system. Developing nations and developed nations pay different postage rates. Developed nations like the United States, Germany, and Japan pay higher rates. Developing nations like China pay dramatically lower rates as a development subsidy. This single classification created massive structural arbitrage. By 2005, a small electronic component, a microchip or connector, weighing 50 grams, shipped from Shenzhen to New York, cost approximately $1.50 in postage. The same component, shipped within the United States, cost $4.75 in domestic postal rates. Chinese manufacturers could mail packages across the entire Pacific Ocean for 1/3 the cost of American domestic transit. Chinese manufacturers capitalized on this cost delta with absolute precision. Rather than consolidating components into large container shipments, they shipped thousands of individual envelopes daily. A single factory mailed 50,000 component envelopes per week directly to Western distributors. Each envelope avoided container shipping costs, port handling fees, and international freight brokers. Chinese factories shipped components globally for 2 cents per unit. Western manufacturers paying domestic postal rates could not compete on price. Between 2001 and 2010, this postal arbitrage generated approximately $150 billion in cost savings for Chinese manufacturers. They did not take this as profit to be distributed to shareholders. They reinvested it into infrastructure expansion. They built new factories, purchased precision equipment, funded engineering talent pipelines. A single year of UPU arbitrage profits funded construction of 500 new manufacturing facilities across Shenzhen and surrounding provinces. Just like China spent 40 years optimization engineering their physical infrastructure, we are constantly tuning our analytical pipeline here to bring you these deep dives with zero fluff. If you want to keep tracking the invisible mechanisms that quietly control global wealth, hit that subscribe button, drop a like, and leave a comment below on whether you think the West can ever truly decouple. It trains our algorithmic loop to deliver more high-utility breakdowns straight to your feed. Now, let's look straight back at the turning point, the exact moment China pivoted from cheap assembly to becoming the unstoppable tech and manufacturing leader it is today. By 2008, the Shenzhen cluster had matured beyond low-cost assembly. Wages were rising. The postal arbitrage was being eliminated through UPU treaty reforms. The old model, cheap labor and postage arbitrage, was no longer viable. China executed a strategic pivot, transition from quantity to specialization, from cheap to elite manufacturing. BYD, a Shenzhen manufacturer, became the world's largest producer of electric vehicle batteries. This is not low-margin assembly work. EV battery manufacturing requires advanced chemical engineering, precision electrode fabrication, thermal management systems, and safety compliance testing. BYD did not win through low labor costs. They won because 40 years of accumulated manufacturing infrastructure, supply chain partnerships, and engineering talent were concentrated in a single geographic cluster. DJI, another Shenzhen company, captured 75% of the global consumer drone market. Drone manufacturing requires precision machined components, advanced motor design, flight control software integration, and regulatory compliance across 180 countries. DJI did not win through cost. They won through engineering velocity. A San Francisco competitor takes 18 months to design and prototype a new drone. DJI, with suppliers and testing facilities 6 blocks away, takes 6 months. But the real infrastructure moat is rare earth processing. Every electric vehicle motor contains permanent magnets made from neodymium iron-boron alloys. Every drone motor uses these high-intensity neodymium magnets. Every advanced radar system, military targeting computer, and wind turbine generator depends on permanent magnet technology. Neodymium must be extracted, refined, and processed through a highly specialized chemical pipeline. The refinement process utilizes hydrochloric acid and sulfuric acid, requiring massive industrial mitigation infrastructure to manage radioactive thorium waste products. Producing a single ton of refined neodymium element requires the processing of 2,000 tons of chemical inputs and results in 500 tons of industrial tailings. China controls over 90% of global rare earth chemical refining infrastructure, and virtually the entire global supply of permanent neodymium magnets. Other countries mine the raw rare earth minerals. However, the advanced chemical refinement that converts raw ore into usable magnets is concentrated in China. This landscape is shaped by long-term capital allocation choices and differing regulatory overhead costs. In the 1990s, the United States maintained functional rare earth processing capacity, but shifting domestic environmental compliance costs altered profitability margins, leading Western firms to shutter their domestic refineries. Concurrently, Chinese industrial policy prioritized absorbing these high capital expenditures and processing overheads, integrating the hazardous refinement steps into their domestic industrial foundation to secure an absolute global market share. This creates an unbreakable choke point. A Western company designs an elite motor, but permanent magnets come from China. A Western battery manufacturer builds a factory. Cathode materials contain rare earth elements. Processing them requires access to Chinese infrastructure. A US military contractor designs an advanced targeting system. The permanent magnets inside it? China refines them. The Pentagon cannot build a modern drone motor without purchasing refined rare earth magnets from Chinese suppliers. Vertical integration of extreme processing clustering makes it physically impossible for Western competitors to simply purchase raw ore and refine it locally. The energy costs, toxic chemical handling, regulatory environment, and decades of accumulated refining expertise create barriers that capital and policy cannot overcome quickly. This is the structural bottleneck. It is not a constraint of labor costs or tariffs or trade policy. It is a trap of physical infrastructure. Factory buildings are fungible. You can build a factory in Ohio, but you cannot build 40 years of accumulated supply chain density. You cannot replicate the 50,000 factory ecosystem Shenzhen constructed over 3 decades. You cannot recreate rare earth processing infrastructure without accepting the complex industrial processing footprint that Western regulatory frameworks currently restrict. This is why decoupling fails. It is not that Western politicians do not want to decouple from Chinese supply chains. It is that they physically cannot. Not quickly. Not without rewriting 40 years of infrastructure architecture and accepting decades of reduced manufacturing capacity. A politician can pass a tariff in a day. Rebuilding rare earth processing infrastructure takes a generation. The blueprint of global trade is shifting beneath our feet, and those who control the physical plumbing dictate the rules. Tune in to our next episode, where we will deconstruct another invisible mechanism quietly shaping your world. Until then, keep looking at the plumbing,